Hello and welcome to the web series ZeroPM Pieces. My name is Sarah Hale and I'm the project coordinator of a really exciting new research project called ZeroPM. In the ZeroPM Pieces, the researchers in the project will tell you about one piece of the ZeroPM puzzle that they're working on. So without further ado, here comes a ZeroPM piece.
Thank you and welcome to my webinar. My name is Ian Cousins and I'm a professor in environmental chemistry at the Department of Environmental Science at Stockholm University. Today I'm going to provide you with some background on the essential use concept. This is a concept that I've been heavily involved in developing. As we will conduct research in Work Package 2 of ZeroPM on the further development and application of the essential use concept, it's useful to first have some background. The concept started from our concerns over the wide use of per- and polyfluoroalkyl substances, or PFAS, in society. Scientists, including myself, recently started calling for the phase out of PFAS because of concerns regarding their extreme environmental persistence and uncertainties regarding the effects and risks associated with most substances in the class. But there are hundreds of uses of PFAS, and it's clearly impractical to phase out all these uses in one step. We started to consider whether essentiality could guide the phase out. In other words, we might be able to phase out so-called non-essential uses rapidly and allow the essential uses to continue until safer alternatives are developed. But how do we define essentiality and sort out the essential and non-essential uses? Luckily, someone had already thought about this. In the Montreal Protocol, the essential use concept was used to guide the phase out of ozone depleting substances. Uses were only considered essential if they were necessary for health and safety or critical to the functioning of society. So we decided to adapt the Montreal Protocol definitions and apply them to PFAS. In our first paper on the essential use concept, we came up with 3 different categories for uses of PFAS. The 3 categories were so-called non-essential, substitutable, and essential uses. Category 1, or non-essential uses, are those uses that are not essential for health or safety or the functioning of society. Category 2, or substitutable uses, are those uses that have to be regarded as essential because they have important functions, but where alternatives exist, thus making these uses of PFAS no longer essential. Category 3, or essential uses, are those uses that are considered essential by society because they are necessary for health and safety or other highly important purposes for which alternatives are not yet established. Even if a use falls into Category 3, this should not be considered permanent. Innovation in the development of non-fluorinated alternatives can lead to it moving it up to Category 2. Anyhow, based on these definitions, we tried to determine which category various use cases of PFAS belong. And all of this is documented in this first publication, which is shown in the top right-hand corner of the slide. In 2020, the European Commission published the European Union Chemical Strategy for Sustainability. In their strategy, the Commission suggested to apply the essential use concept. However, the Commission wanted to expand the concept beyond only PFAS to the most harmful substances, which presumably includes PFAS, but also a wider range of substances. Most harmful substances are described in the Chemical Strategy for Sustainability as chemicals that cause cancers, gene mutations, affect the reproductive or the endocrine system, or are persistent and bioaccumulative. It's therefore unclear in the Chemical Strategy for Sustainability if it extends to persistent and mobile substances, but we think it should. The point is that the essential use concept should be a precautionary approach applied to those most harmful substances for which traditional risk assessment methods are not sufficiently protective. When applying the essential use concept as we envisage it, it's all about function. So the first question to ask is, what is the function of the chemical of concern in a use case? And it should be noted that there are different aspects of function that need to be considered, as defined by Joel Tickner and colleagues in the concept of functional substitution. Function can be divided into chemical function, end-use function, and service function. For example, let's consider the different aspects of function in the use of PFAS in aqueous film-forming foams used to extinguish fuel fires. The chemical function is that PFAS are surfactants, actually very strong surfactants. The end-use function of this strong surfactant is to facilitate the spreading of an aqueous film that rapidly spreads over the fuel and flames. And then the ultimate service function is to extinguish the fuel fire. The reason to think of function in these different ways is that we can then reveal different opportunities for substitution. The example I want to use is for bisphenol A use in thermal paper, which is in the middle column of the table above from the paper on functional substitution by Joel Tickner and colleagues. Thermal paper is used in paper receipts we get in the stores when we buy stuff. Handling these paper receipts has been shown to be a pathway of human exposure to bisphenol A, which is an endocrine disrupting chemical. If we want to substitute the chemical function of bisphenol A, we could then find a similar chemical that would replace the chemical function. This kind of drop-in replacement is what has often happened for bisphenol A, and it's been replaced, for example, with bisphenol S or bisphenol F. On the other hand, if we want to substitute the end-use function, we could redesign the thermal paper so that it doesn't require the use of bisphenol A anymore. Finally, we could even substitute the service function and ask, do we need paper receipts at all? We could instead replace them with electronic receipts. And I believe this is the direction we're slowly moving towards in society. In our more recent work in applying the essential use concept, we have realised that there are three aspects that need to be considered. And these three aspects do not need to be considered in any particular order. For aspect one considers if the functional use is necessary for its performance in the application. This may seem like an odd question at first, but some chemicals are added to a product or processes when their addition is not necessary for performance. One example is the use of small amounts of PTFE in some kinds of bike chain lubricants. It turns out that the addition of PTFE in low quantities has marginal effect on performance. The manufacturers have told us that writing with PTFE on the label is important for marketing. For aspect two, one considers if the use is necessary for health and safety or critical for the functioning of society. This aspect is the most challenging and controversial to answer because because there can be a range of answers depending on the opinions among stakeholders. We can actually avoid to answer this question if aspect 1 or 3 are false. But to answer this question objectively, we need criteria to define what is necessary or critical. And the Commission are attempting to write detailed criteria and sub-criteria for essentiality, and these will be available soon in the Wood report, as soon as July or August this year. For aspect 3, we need to consider if there are available alternatives for this particular use that are acceptable from the viewpoint of health and safety. There are often alternatives, so aspect 3 is quite often false. In the case of PFAS, at least, because in the many use cases that we have examined, there are often alternatives. If all three of these aspects are true, then the use can be considered an essential use. However, if only one aspect is false, then the use is a non-essential use. In a paper in Press, we're combining the functional substitution and essential use concepts to aid the phase-out of the most harmful substances. This paper is a joint collaboration between Joel Tickner's group, Sang-Yun Wang, Martin Sharing and me. In the middle blue box, you can see the essential use concept and the three aspects from the previous slide. In the yellow box on the left, you can see some of the concepts from functional substitution, such as the three different levels of function on the bottom left. You also see considerations for performance. We may well have to accept lower performance in substitution, but this performance should be adequate for the given use case, or in other words, fit for purpose. In the green box on the right, you can see the various action steps. If the technical function is not needed or there are safer alternatives providing fit for purpose performance, then the chemical of concern can be phased out. Trickiest may be for some stakeholders to accept are those cases where the application is not considered necessary, For example, do we need stain-proof ties if the only way to achieve the stain repellency is to use harmful substances such as PFAS? Finally, for essential uses, we need to encourage innovation for finding safer alternatives, and in the meantime have a risk management plan for continued use of the chemical concern, for example by virtually eliminating emissions. This paper is in Press in Environmental Science and Technology and is an early ZeroPM output. I'll now run you through 3 example case studies for uses of PFAS for which we have applied the essential use concept. So the first case study is the use of PFAS in fluorinated ski waxes. You need ski waxes to ski these long ski races like the 90-kilometer Vasaloppet ski race featured in this photo. In the past, many competitive skiers would have used fluorinated waxes, which are based on fluorinated alkanes. These fluorinated waxes also contain perfluoroalkyl carboxylic acids, or PFCAs, including quite high levels of PFOA, which is listed on the Stockholm Convention. There are no PFAS-free alternatives as good as the fluorinated waxes, but you can ski nearly as fast with the non-fluorinated waxes, which are much better for the environment and human health. You don't need to ski 5% faster. The alternatives are therefore fit for purpose, as well as safer for the environment. It's therefore considered a non-essential use, and now the International Ski Federation, or FIS, has agreed to ban fluorinated waxes from competitions. It took a couple of years, though, to confirm the ban because there wasn't a good way for testing if the skiers were using fluorinated waxes and therefore cheating. For next season, there are suitable testing methods and fluorinated waxes will be banned from competitions. The second example is the use of PFAS in aqueous film-forming foams, or AFFs, for extinguishing Class B fuel fires. AFFs have been used since the 1970s and resulted in high contamination, especially around commercial airports and military bases. It's been a huge disaster in many countries around the world, including in Sweden, Norway, the US and Australia. So-called fluorine-free Class B foams, or 3F, have been available since the early 2000s and apparently meet the standard firefighting performance certifications. Note that these 3F alternatives use a different end-use function for extinguishing the fuel fires and are not considered aqueous film-forming foams. Many commercial airports have recently phased out AFFs and used 3F instead. Still, there is some debate if AFFs are needed for certain scenarios. The military in many countries still argue that 3F are not fit for purpose and continue to use AFFs. Some departments of defence argue that for rapidly putting out large fuel fires, there's no viable substitute for AFFs. So the military consider AFFs an essential use on the basis of safety, whereas commercial airports consider AFFs as substitutable. A final example is an area that we've worked on in my research group. Textiles are sometimes treated with a type of polymer known as a side chain fluorinated polymer to provide liquid repellency. As well as in rain jackets, these coatings are also used in occupational protective clothing, for example medical gowns, military apparel and firefighting turnout gear. This figure shows that increasing protection requirements are needed for different types of clothing. If you're going to the beach, then maybe you don't need super high protection, but if you're climbing Mount Everest, you'll need protection against biological fluids in the case of medical workers, or moisture and heat in the case of firefighters, the protection requirements are higher. Some garments have likely been over-engineered. For example, do we really need water-resistant surfer shorts? We clearly need water repellency in outdoor clothing and equipment for safety reasons, but this can be achieved with PFAS-free alternatives. For a few applications where protection is essential against fluids of a wide range of polarities, the uses of PFAS are currently essential, and innovation is needed to find suitable PFAS-free alternatives. On the other hand, one could question whether we men need stain-proof ties, even if we cannot find an alternative to PFAS that provides stain repellency. Stain-proof ties are not, in my opinion, necessary for health and safety or critical for the functioning of society, and maybe we should instead work on our table manners. So hopefully you agree that the essential use concept can guide the phase out of the most harmful substances. The concept does not necessarily have to be applied in regulation alone. Indeed, many of the substitution of PFAS have been led by industry albeit with the overhanging threat of regulatory pressure. The phase out of PFAS in adult clothing, ski waxes, firefighting foams, non-stick cookware, film forming agents, and many more uses have occurred without regulation. Industry are sometimes portrayed as bad guys, but there are many good actors in industry who are interested in phasing out PFAS from their products. Many companies have joined the ChemSec PFAS movement, and others have joined the POP3 project led by RISE in Sweden. In the POP3 project, which is truly inspiring, companies work together and innovate to phase out PFAS from their products. This figure shows the parallel push by some parts of industry to phase out PFAS along the supply chain, combined with the pull applied by regulation and NGOs. This is, as I say, a parallel process which works in tandem. Although there's been much recent progress, there are certainly challenges remaining, and these will be tackled in the ZeroPM project. Firstly, for uses that are considered substitutable, we must be careful not to introduce regrettable substitutions. This is why we're investing considerable effort into novel alternatives assessment methods in Work Package 2 of ZeroPM. Secondly, how does society decide when uses are essential or non-essential? We're often told that this is a question that society needs to answer and that we cannot answer it with detailed criteria or scientific methods. Luckily, we're only left with the challenge of determining essentiality if there are no alternatives. And often there are alternatives. In those cases where there are no alternatives and there is a grey zone in determining if a use is necessary for health or safety or critical for the functioning of society, then there is a challenge of determining essentiality. I personally think these use cases are relatively few, but for those cases, detailed criteria for essentiality are being developed by the Commission and will be available in the Wood report in the next couple of months. In Work Package 2, social scientists from the University of Vienna will be determining stakeholder views on essentiality for various use cases, which will help us better understand if the type of criteria developed by the Commission are reasonable or not for stakeholders. So that concludes my introduction to the essential use concept. Please follow our progress on developing and applying this concept to multiple use cases in ZeroPM. Thank you for your attention, and I'll be glad to take any questions that you may have.
ZeroPM, Zero Pollution of Persistent and Mobile Substances. This project has received funding from the European Union's Horizon 2020 Research and Innovation Programme under Grant Agreement number 101036756.